Greetings, everyone. My name is Urania Spantili, and today I will present to you our work titled How Much is Too Much Error? Analyzing the Impact of Approximate Multipliers on DNNs. Over the past decade, deep neural networks, or DNNs, and specifically convolutional neural networks, have been used in many applications. Nowadays, applications are very likely to be based on image classification tasks. They might require depth and hand pose estimation on top of image classification, and overall, they could potentially require tasks such as speech and image recognition and more. Embedded devices are being put to the test by the ever-growing computational demands of modern DNNs. They are now called to integrate DNN accelerators as a solution to the throughput latency requirements. Integrating thousands of Mach units, however, results in increased energy consumption. How can we trade off the system's energy efficiency with respect to the DNN's accuracy? A great amount of NN computations can tolerate at least some degree of approximation, thus reducing energy consumption without sacrificing the NN inference accuracy. By designing and developing approximate multipliers, we can achieve considerable energy reduction with respect to the entire accelerator. Current techniques for designing approximate multipliers mainly focus on the introduction of low error and apply retraining to recover the accuracy loss. This is not always feasible, however. In this work, we investigate the impact of approximate multipliers when applied to different layers of the same DNN across multiple datasets. We consider approximate multipliers and explore how more and less aggressive multipliers, in terms of mean relative error, affect DNN accuracy during inference when they are applied to separate layers. We employ collaborative filtering techniques to predict the behavior of any given approximate multiplier on a specified DNN and dataset. We propose a low overhead and time-efficient procedure that provides information regarding approximation-induced error per DNN layer given any approximate multiplier without the need to employ exhaustive exploration methodologies. Today, we will first show how we will be assessing approximate multipliers throughout this work. Next, we will show an overview of the proposed framework and its flow. Finally, we will show how we utilize collaborative filtering techniques to predict approximation-induced error in different DNN layers. When it comes to approximate multipliers, each bit has a different weight and arithmetic error metrics are utilized for this reason. In this work, we categorize approximate multipliers based on their mean relative error, which is derived from the mean absolute error metric. Specifically, when we replace the exact multiplication with an approximate one during DNN inference, the mean average error would be acquired as shown in equation 1, and the MRE value would be calculated by replacing the error distance in equation 1 with the relative error distance. The MRE value is shown in equation 2. In both equations, accurate of x represents the exact multiplication x between a weight and an activation, while approximate of x represents the approximate one for a total of n operations. We use the MRE metric to select 8-bit power error Pareto optimal multipliers from the EvoApprox library that have MRE values below 100%. This table shows the utilized multipliers alongside their respective MRE, which ranges from 0.01% up to 99.22% in an attempt to deeply investigate the impact of varying MRE values on different DNN layers. Note that an MRE value of 99.22% means very high approximation, and the respective multiplier would not be able to be applied to an entire DNN without resulting in unacceptable accuracy results. Therefore, only a layer-wise mapping technique would be able to utilize such high MRE multipliers. Also note that a high MRE percentage results in most cases in high savings in terms of energy too. This figure shows an overview of the proposed experimental setup. For each target DNN, we first extract its number of layers m. We apply approximation only on layer 1 by using one by one the multiplier shown in this table. We monitor the inference accuracy while the remaining layers remain mapped to the exact multiplications. Next, we apply approximation with the same approximate multiplier to layer 2, while layers 1 up to m are mapped to the exact multiplier. We continue the same procedure with the same approximate multiplier until only the last layer is under approximation, while the exact multiplier is used for layers 1 to m-1. For each run, we monitor the inference accuracy for the selected approximate multiplier. We stop the procedure once all the approximate multipliers in the presented table have been evaluated for all the layers of a target DNN. We have now constructed a database of accuracy observations. We then leverage these past observations to identify similarities with new observations through collaborative filtering techniques. From the 40 initial multipliers, we keep 32 of them as our training set and 8 of them as a testing set, splitting them in an 80 to 20 manner, as commonly used in literature. For a DNN with m layers, we build a 32 by m matrix A, where each entry contains the accuracy drop, AD, of each approximate multiplier on each DNN layer, with the rest being mapped to the exact multiplier. This matrix is called a utility matrix. To predict the AD values per DNN layer for a new multiplier, we will sample only some of the DNN layers, resulting in a sparse matrix. The two main methods that will be used are singular value decomposition and PQ reconstruction. Singular value decomposition identifies similarity concepts on matrix A like so. After decomposing matrix A, we apply PQ reconstruction to fill in the missing values of A. If R is the rank of matrix A, then PQ reconstruction will result in these two matrices, where this relation approximates the initial matrix A and fills in the missing values. We evaluated 4 DNN models across 4 different datasets. However, the question that arises at this point is, which layers should be selected for sampling in the previous steps? From the information that has already been gathered, we can make several observations that can assist in making this decision. From the already acquired information, we can determine which layers are more sensitive to approximation and which layers are more resilient. For this example on GoogleNet, we can observe that layers 1 and 3 exhibit high accuracy drop, while layers 4 and 19 are shown to be resilient to error. Therefore, for each new multiplier that has not been encountered in the past, we sample the output accuracy of the GoogleNet only for layers 1, 3, 4, and 19. We will now present our evaluation setup. As mentioned earlier, we split the 40 multipliers taken by the EvoApprox library and end up with a test set of 8 multipliers. For each of the considered DNNs, we decide the sampling layers following the example described in the previous section. Specifically, we selected 4 sampling layers for the ResNet 20 and GoogleNet networks, 7 layers for the ShuffleNet network, and 2 layers for the VGG11 network. Our goal was to select roughly 20% of the total DNN layers as our sampling points, where half of them would be resilient layers and the rest of them would be sensitive. The 8 multipliers we sampled were selected randomly from the initial pool of multipliers in the table shown here. We conduct our evaluation on 4 datasets, CIFAR 10, CIFAR 100, GDSRB, and LISA. The classification difficulty across these four datasets varies since the number of classes ranges from 10 up to 100. For instance, it is expected that the inference accuracy of any given DNN for the CIFAR10, GTSRB, and LISA datasets will be higher when compared to the CIFAR100 dataset. This figure shows the observed prediction error when using the employed collaborative filtering techniques for the ResNet 20 network for all four datasets. The multiplier IDs are sorted based on their MRE. It is evident that the prediction error is higher for the higher MRE multipliers and remains below 5% for the first 5 multipliers across all four datasets. This figure shows the respective prediction error results for the GoogleNet. Again, in this case, the higher MRE multipliers show high prediction error, especially in the case of the CIFAR100 dataset. Overall, the behavior of GoogleNet seems to be easily predictable for the selected multipliers. On the contrary, the VGG11 network was proven to be the most unpredictable among the considered DNNs, as shown in this figure, showing high prediction error specifically for the CIFAR10 and CIFAR100 datasets. Finally, this figure shows the results for the ShuffleNet network. This network displayed low prediction error for the GTSRB and LISA datasets. However, the multiplier with the highest MRE resulted in up to 9% prediction error for the CIFAR10 and CIFAR100 datasets. So, how time-consuming is the proposed methodology? Triggering the described collaborative filtering techniques to obtain predictions is not a time-consuming task overall. The entire procedure consumes less time than running the DNN inference for any of the considered networks on any of the described datasets. Therefore, instead of running a full exploration on all of the layers of a target DNN, we can run the inference on just the 20% of the total layers. As an example, consider the ShuffleNet network, which comprises 37 layers. Assume we want to acquire information regarding its per-layer error behavior for the CIFAR10, CIFAR100, GTSRB, and LISA datasets. One would need to trigger the inference phase of the DNN a total of 4 times 37, that is a total of 148 times. Instead, by only sampling 7 specific layers, the inference phase would be triggered a total of 4 times 7, that is, a total of 28 times. Deep neural networks have been imposing substantial challenges on embedded devices with limited resources. Approximate computing has gained a lot of research attention as a computing paradigm that achieves significant energy efficiency gains by relaxing the need for completely accurate DNN performance. In this work, we conduct an in-depth analysis of the impact of approximate multipliers on different DNN layers. We leverage the layer sensitivity information to build a matrix, and we apply collaborative filtering techniques to predict the accuracy degradation inflicted on a target DNN when selecting different approximate multipliers. This work aims to bridge the gap between approximate circuit design and DNN accuracy by providing useful insight into the impact of approximation error on DNN inference. Thank you very much for your attention, and I would be very happy to address any questions you may have.